Welcome to this lecture about geothermal systems for heating. In this lecture, we will address both shallow and deep geothermal systems. There is not a clear definition of when a geothermal system is shallow or deep, but we can consider that systems that do not go deeper than 200 meters are shallow ones. Let's start with the shallowest of them, earth tubes and ground heat exchangers coupled to heat pumps. Earth tubes are passive systems in which the outdoor ventilation air is circulating through pipes in the ground. The air is then heated by the ground, which in winter is warmer than the outdoor air. Similar systems are used by having the air circulating in a warm basement. As for the sizing of these pipes, which may need quite some length, you need to look at the conduction heat transfer between the pipe and the ground and the convection heat transfer in the pipe. These estimations are beyond the scope of the course. Next to this, there are also the ground heat exchangers, used as a heat source for the heat pump. You see them on the right in vertical and horizontal design, and their connection to the heat pump was studied in another lecture. For these heat exchangers, it is important to be aware that the space between the tubes should be large enough to avoid the ground to cool too quickly. You can imagine that the ground cools down around such a pipe, so the other pipes or the further spirals should be placed far enough from this cold bubble. Even more important is to make sure that the ground has the ability to recover enough heat during the hot season. Otherwise, it would become colder each year and the performance of the heat pump would decrease a lot. So, these systems work well when there is a warm season long enough to regenerate the ground temperature. Alternatively, this can be aided by using the heat pump as chiller in summer and delivering the condenser heat to the ground heat exchanger. There are also systems in which a solar boiler is used to deliver additional heat to the ground during summer. Which brings us to the aquifer thermal storage systems, in which this problem of balancing the temperature in the ground is turned over into a great solution. Although they are much deeper than the heat exchangers we just described, aquifer thermal energy storage systems, so-called ATES systems, are generally considered as being shallow. What is an ATES and how does it work? In an ATES system, water has to be pumped from the ground in order to make use of the heat it contains. An aquifer is a layer of permeable porous rock, clay, gravel or sand that contains groundwater. Their hydraulic conductivity and porosity describe the ease with which water can flow through it and therefore also the ease with which it can be pumped. Clay has a much lower hydraulic conductivity than sand or gravel, by which it is very difficult to pump the water contained in a clay aquifer. Therefore, ATES systems make generally use of aquifers in sand or rock. The water circulates slowly between blocks of sand or rock and can be pumped. To make sure that the aquifer layer remains stable, it is mandatory to re-inject the same quantity of water that has been pumped into the ground. Generally, the depth of such systems is no more than 150 or 200 meters. Let's start with the summer situation in which cooling is needed for the building, and just imagine we want to cool warm outdoor air from 35 degrees Celsius to 20 degrees. If we pump the cold water from the aquifer, we can easily transfer heat from the warm air to the aquifer water flowing through the heat exchanger. In this picture, I used aquifer water at 9 degrees, which is often the temperature in North Europe. But that would work as well if the aquifer was warmer, as long as its temperature is colder than the one of the outdoor air. So, the cold water from the aquifer is pumped and heated by the warm air up to 20 degrees in this example. This aquifer water at 20 degrees is then re-injected into the aquifer using a well placed far enough from the cold one, generally a few hundred meters. This pumping of the cold aquifer water is done all summer, resulting in a bubble of warm water at the cold well. At the warm well, sorry. I remind you that the water is somehow confined within the sand and circulates only very slowly between the packages of sand. As sand's thermal conductivity is not very high, the bubble of heat is able to remain for a few months. And then winter arrives, where we need heat. The heat that has been stored in the warm well can then be used by just reversing the flows in the heat exchanger. Now, the warm water is pumped to the heat exchanger, in which it gives its heat to the cold outdoor ventilation air in such a way that it is nicely preheated, for instance, from 5 degrees to 15 degrees. In our example, we used a cold well at 9 degrees and a warm well at 20 degrees. Other temperatures could be chosen depending on the desired temperature levels. It is even possible to store high temperatures above 40 degrees. This is not often allowed, as this could change the chemical balance in the ground. In general, there are temperature limitations, and for instance in the Netherlands, it is forbidden to go above 25 degrees. It is also mandatory to make sure and to demonstrate that there is a thermal balance in the ground, meaning that the quantity of heat extracted is the same as the quantity of heat supplied to the ground. A yearly balance must be carried out. Be aware that these systems in fact do not even use the heat from the ground. They just store cold and heat from the building and the outdoor air. And last but not least, an even better system is to use the warm aquifer water as a heat source for a heat pump. Because the heat source has now a very high temperature, the COP will be high too. Typical COPs for these systems in the Netherlands are around 6 to 8. And the EER also. And last but not least, it seems very impressive, but such an ATES system looks like from the outside is just like that. The cover of a sewage system. This is one of the ATES systems on our campus. In the Netherlands, thousands of these systems have been installed as they are relatively cheap and offer a form of free passive ground cooling. There is just a pump needed to pump the groundwater. Deep geothermal energy is thermal energy generated in the core of Earth. Temperature differences between the core and the Earth's surface drive the continuous conduction of heat to the surface. The temperature of this heat is not equally distributed. For instance, in Iceland, temperatures of more than 200 degrees are observed at less than 1 kilometer depth, while in the Netherlands, temperature at that depth is only 40 degrees. Just like for the aquifer thermal storage, all water or steam that is extracted should be refilled in order to maintain the geological balance and to not induce pressure differences that could lead to earthquakes. In the picture left, you see such a geothermal plant with 2 wells to extract warm water and 1 to reinject it. One point of attention for the future is that a cold bubble is created around the injection pipe, which could disperse towards the warm well. It is believed that after 20 to 50 years, such a geothermal system would have to stop because of this. However, there may be also possibilities of regenerating the layer by boring a new well a bit further. In the heat exchanger above the ground, the hot groundwater or steam gives its heat to a hot water distribution pipe connected to district heating. In systems like the dry rock enhanced geothermal system that we have shown on the picture, only 1 pump is needed in the injection well. The pressure in the Earth core is much higher than the atmospheric one. In the extraction wells, no pump is needed. Such geothermal systems can provide water at 40 to 70 degrees like in the Netherlands, but also at much higher temperatures like in Iceland or Switzerland and many other places all over the world. When the temperature is above 100 degrees Celsius, it is even possible to use the steam to produce electricity, which will be treated in another lecture. The concurrent production of heat and electricity makes such a system much more affordable. Such a geothermal system is relatively expensive as the tariffs are around €1,000 per meter. Boring down to 3 kilometers and using 2 wells would lead to an investment of 6 million. These systems are generally used to heat complete districts or cities and are never used solely at building level. Such deep geothermal systems are difficult to control. In fact, they cannot be stopped or restarted that easily. That is why a lot of research is done to look at combinations with aquifer thermal storage. You see in this figure the heating demand of a building or a group of buildings from winter to summer. If the geothermal plant is designed to produce the maximum needed power, there will be in summer an enormous quantity of heat produced that cannot be used, except if it can be used as heat to power an absorption chiller. That will be treated in another lecture. It is therefore better, in general, to size the geothermal plant smaller and to store the heat produced in summer in an ATES system, for instance, in order to reuse it during winter. In this lecture, we described three systems: the shallow geothermal ones, which are ground heat exchangers used with heat pumps. As the ground is at a high temperature source, the COP of the heat pump is high. Alternatively, in small buildings, earth tubes may be used to preheat cold outdoor air, but that's not very efficient. Concerning aquifer thermal energy storage, we have seen that these systems are able to store cold in the ground in winter that can be used in summer, and to store heat in the ground in summer to reuse it in winter, often in combination with a heat pump. These ATES systems have very high cooling and heating efficiencies. Finally, the last system was about deep geothermal energy, the potential of which is very high worldwide and will help to realize the transition to renewable heat systems. It cannot, however, be realized at building level and necessitates infrastructural works like boreholes and district heat pipes. Thank you for your attention.